Go. So this lecture is titled Analyzing Quadratic Functions. But like I said, we're going to be reviewing a lot of concepts that take us back to test one and then even some of the stuff that we've been doing with solving quadratic equations here. And we're really putting it to work because I think up to now, it kind of has felt like we're just doing random operations on these different polynomial things. There's a lot of letters, there's a lot of numbers. You have to remember a lot of processes. But like there's a reason why we give you these tools, and it's all about analyzing quadratic functions. So our objectives for today are to sort of unveil a little bit of vocabulary and take us back to the world of graphs. So the reason why we've been studying quadratic equations is because we want to really understand a quadratic function. So a quadratic function um, is basically a quadratic equation that can generate a graph for us. So we want to be thinking about, as all functions, we're going to plug in an x value, and then we're going to figure out what our y value is by evaluating that function. It just so happens that that function is a quadratic equation. Okay. And so we want to review some of our ideas like transformations of quadratic functions. You guys remember when we looked at like shifting a graph up and down versus left and right, and also vertically stretching the graph versus vertically compressing or shrinking the graph. Those concepts are going to come up. Then we have some other vocabulary that's very specific to quadratic functions. Um, so let's just get into it and see how things go. Okay. So first, a quadratic function is a function that takes the form um, f of x is equal to ax squared plus bx plus c. Okay. So we call this the standard form of a quadratic function. Okay, so I'm just going to type that on the screen so I don't have to write it with my mouse. Standard form. Okay. But this shouldn't be a new concept, right? Because since we've been sort of factoring polynomials and factoring quadratic trinomials and solving quadratic equations, whenever we had ax squared plus bx plus c equals 0, we call that standard form. Okay. So this isn't new. You should be able to recognize your coefficients like a, b, and c, and those will just be numbers that differ from problem to problem. Okay, we don't want to like get too focused on those numbers because we really want to focus on the process. Okay, so whereas when we were studying quadratic equations, I told you guys that those are second degree polynomial equations. A quadratic function we call a second degree polynomial function because the highest degree is 2, or the highest exponent is 2. So that's why we call this a degree 2 polynomial. Okay. And a linear function, when we were graphing straight lines, those were degree 1 polynomial functions. We just didn't use this fancy language to talk about them that way. Okay. You can easily identify when we have a quadratic function because you're looking for that squared term. Remember the etymology lesson I gave you? Quadratic comes from the Latin quadratus, which, if you are vaguely familiar with Spanish, cuadrado means squared. So using that kind of logical jump, we can get to, if we have a squared term, it's quadratic. Okay. But what we're going to get into is this fact that when we graph quadratic equations or quadratic functions, you're always going to get a U-shaped graph. And that U-shaped graph may be right side up or it may be upside down. So if we look at this picture that I have on the left, this is upside down compared to this U-shaped graph, which is right side up. Okay. And these shapes, these U-shaped graphs, are called parabolas. So when I'm talking about a parabola, I'm talking about the graph of a quadratic function. Okay. Kind of a lot of vocabulary to throw at you here, but it won't be too bad. What I want to do right now, though, is go to pencil and paper because I think, me drawing on the PowerPoint is one thing, but me drawing some things, giving you guys a chance to digest what I'm talking about goes a little bit better, I think, when we're on pencil and paper. So let's go with this. Quadratic functions. Um, Standard form will be f of x is equal to ax squared plus bx plus c. Okay, we'll call that standard form. And remember that these functions are a machine that you can choose any number from the number line. We think of the x-axis as being our regular number line and plug it into the machine for x. So x is the input value that we choose. Okay. And then, like we did in test one, in preparation for test one, we plugged things into a function and then we substituted that in for x. And then this gets evaluated, right? Or simplified if you want to think about it, right? We just put it in our calculator and then that spits out our y value, which is our output value. So that's what I mean by these functions are machines. You're putting something in, it's doing some math, the calculator's doing some math, and then it spits out the y value. And then once we have an xy pair of our input and output, well, then we can take that to a graph and plot it. Okay, so that's kind of how we're going to be building these graphs. Okay, let's see. Okay, so I kind of want to start off with an example here. Kind of make one up on the fly, if you guys don't mind. Hopefully I have enough room here. I think it'll be fine. Let's say that we're going to start off with f of x. This is example one. F of x is equal to, and we'll start off with something easy like x plus 2 squared minus 3. Okay. Give you guys a moment to write that down. Okay. Now, pretend that this is old school where we do not have a calculator, we don't have a graphing calculator. We're not going to just plug this into a website and graph it. We want to do this by hand just so we understand the process of graphing, right? So transport us back to the days of high school when your teacher asked you to do this. Can anybody tell me what is the first thing that I need to do before I can even think about graphing this? Right? Because I want to draw a picture of this graph, but like, how do I make that picture? Where do I begin?
Need to get it into standard form.
So when we were solving quadratic equations, we definitely wanted to get that into standard form. But with these functions, we don't necessarily need them in any particular form to graph. So that's actually a good thing to point out here. So graphing does not require standard form. It doesn't matter what form the equation is in, we can begin graphing, but we need to supply the function with something before we can graph.
So do you input your for X?
Yeah, you just choose your input values, which can literally be anything, and then you just plug it into the equation, whatever that happens to be. So this one was written in standard form. Clearly, this one is not, but it doesn't matter. You're going to choose an input value for x, plug it into the equation. It's going to spit out your y value. So we'll get our xy pair, and then we'll graph it. Okay. So if that's okay to understand, then I would say let's organize ourselves. So I like to organize myself by making a table of my x values that I'm going to choose and then the y values that I'm going to find by plugging those x values into the equation. Are you guys okay with that?
Yes.
Okay. So choose a number. What number do you guys want to use for x?
1.
Sure, we could choose 1. I'm going to put 1 here. And if we plug 1 into this equation, remember that would be like evaluating f of 1, which, you don't have to necessarily write that. I just wanted to sort of bring back that notation. What we're really doing is plugging 1 in for x. So we're going to have 1 plus 2 squared minus 3. And then the calculator is going to give me my y value, right? Or if it's a simple enough problem, you could do it in your head or do it by hand, but I say just grab the calculator and type in exactly what we wrote. So 1 plus 2 squared minus 3 is 6. You guys okay with that?
Yes.
Okay. So that means we now have the ordered pair 1, which was our x value that we chose, comma 6, and we could plot that point. Are you guys okay with that?
Yes.
Okay. Now, you can choose any other number. We've used 1. Any number should work here. It doesn't really matter. And I always tell students that graphing a function takes a little bit of finesse. And what I mean by that is sometimes choosing x values can help make the picture clearer, and choosing other x values will not make it as clear. So with quadratic functions, what I would say is pay attention to this expression inside the parentheses, right? Because in the past I've said whenever you can plug a 0 into a function, it makes the math really easy. So keeping that in mind, if I'm looking at x plus 2, what could I choose for x so that this entire expression turns into 0? What could I choose for x? In other words, what plus 2 would give me a 0?
-2.
Negative 2. So I'm going to choose a -2 for my next point. Okay. And I'm going to come back to why exactly we chose -2 for this problem, or why we were looking at this expression inside the parentheses, but it'll make sense in a moment. We're just going to kind of leave us on a cliffhanger right there. For now, we just need to evaluate the function by plugging in -2. So again, you could write it as f of -2 if you wanted to, although those are just instructions, right? What we're really doing is putting our parentheses, plugging in -2 plus 2 squared minus 3, and then using the calculator to evaluate that. Okay, so what do we get? Let me grab my calculator. And then we did parentheses -2 plus 2 squared, don't forget the square, minus 3. And I got -3. Are you guys okay with that? Okay. So that means my x value is -2, my y value is -3, -2 comma -3. That is one of the points for my graph. Okay. Any questions about what we're doing up to this point? Okay. All right. Well, when we were graphing linear equations by hand, you may remember that I said we only need to find 2 points to graph any straight line. Well, when we're dealing with a second degree polynomial equation, you want to choose one more x value than the degree or that highest exponent in your function. Okay, so technically we need to choose 3. You'll see when you get into Alex that Alex actually does a lot of the work for you, and you really only have to find 2 points. But just to be thorough here, let's choose a third x value just to get an idea of what we're doing here. So we chose 1, we chose -2, and I'm going to choose this one for you guys because, well, I kind of want my numbers to be symmetric. So if I think about -2 as like being in the middle of my graph, okay, then 1 would be, I don't know, like three numbers up. So it'd be like -2, then -1, 0, and then 1. So if I go down three values, then I'd be at -5, I think. Hopefully I chose this correctly. I'm just choosing -5 for no particular reason other than if we look at these numbers on a number line, they're evenly spaced apart, right? You'd have to go up 3 to get a +1, and then you'd have to go down 3 to get the -5, okay? I'm just trying to evenly space my points, okay? So I'm going to go with f of -5, plug that into my function. I get -5 plus 2 squared minus 3. And then we get, well, we grab the calculator and let that do the work for us because it's been a long day. -5 plus 2 squared minus 3. And I got 6 again. Okay. And maybe that's some of the magic that I know how to choose because I'm the instructor of this class. But notice that when I plugged in -2, I got 3. And then when I plugged in 1, I got 6. And when I plugged in -5, I got 6. So, this graph is perfectly symmetrical, or the numbers seem perfectly symmetrical. Let's see what it looks like when we actually graph these points. Okay, so I have -5, comma 6. Okay. Any questions about finding those points? Okay. I just see Audra's thumb emoji just float in the screen every time, so it's becoming kind of a bit, and it's making me laugh. Okay. Um, if we're graphing this by hand, it doesn't have to be pretty. All we really want to do is draw an x-axis here that captures the x values that we have here. So on this number line, we need to go from -2. I'm going to put -2 over here. So let's say 0 is over here and 1 is over here. So mine's kind of like off to the skewed to the left a little bit because I need more negative numbers than I need positive. So this is going to be 1, 2, 3, 4, and then -5. These are all negatives. Okay, and then I just needed to go to a +1 for my x-axis. And then for my y-axis, we need to go all the way up to 6. So maybe I'm going to count by ones. That's fine. 1, 2, 3, 4, 5, 6. Okay. Would you guys like me to zoom into this a little bit more? I don't know if it'll be too zoomed. Is that better? Okay, we got the thumb emoji from one student. Got it. All right. So now that we have our points, we can go ahead and plot these. So the first point that we have is at 1, comma 6. So it's way up here. Got that one. -2, comma -3. Oh, I needed to go down on my y-axis actually. So I need to go down here and call this -1, -2, -3. So we need to go -2, -3, which is down here. I'm just putting little dotted lines to sort of help me line this up. -2, -3, plotted. That one's good. And then -5, 6, and this is a +6. So we're going to go -5 and then up until we reach 6. And that's good enough. Okay. Notice that if I were to connect these with a straight line, I would get like a V shape, but these quadratic functions should be a parabola, which is a curved U shape, and that U should sort of fit and pass through these points kind of smoothly, okay? So I'm just gonna do my best to draw a U that goes down to touch that point down there at the bottom. It might be a little bit pointy. This doesn't have to be perfect. It's not an art class. But then we're going to scoop that back up and come over here and sort of cross through this other point, and then put some arrows on the tops of my U's there. Okay. So this red graph here is the graph f of x is equal to x plus 2 squared minus 3. That's what it looks like. Okay. All right. Now, in the PowerPoint, uh, I mentioned that, or the image mentions that there are some features of this graph that we need to be aware of. The first feature that we need to be aware of is this point right here at the very bottom of the graph. Okay. This point at the very bottom of the graph is called the vertex of the parabola. Okay. And if the graph opens up, that is, if it's a right side up U, we say that this vertex, since it's at the bottom of the graph, that's going to represent the minimum of the function. Okay. And that should make sense. So that vertex is kind of like the central point. It's either going to be at the very bottom of the graph, but in other parabolas, if they're upside down, it's going to represent the very top of the graph. Okay. So it can either be a minimum or a maximum. In this case, it is a minimum. Okay. Then there's another feature that you're going to be asked to find for the graph, and that is something called the axis of symmetry. Okay. And so the axis of symmetry is basically, if you think about your definition of symmetry from grade school, if something is symmetrical, that means that you have a shape or an object that if you fold perfectly in half, that the two sides basically kiss each other, that they land perfectly on top of each other. In other words, if you were to cut this parabola in half, and I'll just put a little dashed line cutting through this halfway mark, right? If I cut through the vertex, that cuts my parabola into two perfect halves that if you were to fold them over that line, they would be overlapping. Okay. That line is called the axis of symmetry. Okay. And we write the axis of symmetry as an equation, and that equation is always going to be x is equal to whatever x value this perfectly straight line that cuts through the vertex goes through on the x-axis. So where did this dashed line cut on the x-axis? What number did we cross?
-2.
Yeah, so x equals -2. That's the axis of symmetry for this particular graph. Okay. Okay. And so like we're going to end up doing some practice problems in here, looking at finding the vertex and finding the axis of symmetry for some different quadratic functions. Okay, so if this felt like it was all over the place, all I'm trying to do is introduce to you guys this concept of the vertex being this central point at either the very bottom or the very top of a parabola. And this idea of the axis of symmetry, this vertical line that we could draw that cuts the parabola in two perfect halves, and we write it as an equation, x equals -2 in this case. Okay, so does anybody have any questions or comments before we do move on to our next example? Okay. All right, well, let's go back to the PowerPoint. Okay, so like I said, our parabolas will either open up or open down. If it opens up, like this one on the right, then the vertex is going to be this point at the very bottom of the graph, so we call it the minimum. If the graph opens down, like this one on the left, down, then that vertex is going to be the highest point on the graph, and so we call it a maximum value. Okay, but either way, the axis of symmetry is the line that we can draw that cuts straight through that vertex and cuts the graph into two perfect halves. Whether it's upside down or right side up does not matter. That axis of symmetry always cuts your graph in half. Okay, so let's see. Um, Many quadratic functions may be written in factored form. So factoring may play a role in solving some problems, but for now, you just need to understand that if it's in standard form, like ax squared plus bx plus c, it's possible to factor that. And whenever necessary, I will show you an example where that can make some of the math a lot helpful, a lot more easy to get through, okay? So now we're going to back up a little bit before we do our first example here. In test one, in module one, we introduced this idea of a bunch of different parent functions. And one of the parent functions was the parent of all quadratics. And you can call that the squaring function. The reason why it's called the squaring function is because it is a function that's written as f of x equals x squared. And all this function is doing is taking this x value, whatever x value is given to it, you square that, and then that's how you get the y value. Okay, so that's why we sometimes give it this common name, squaring function. So negative 2 squared gives you positive 4. 0, if I were to square that, it gets me back to 0. If I square 2, that gets me back to 4. Okay. So if we're looking at this graph, which has already been made for us over here on the right, then this point right here in the center of our parent function is 0, comma 0, because it's at the origin, right? All of your parent functions basically started off with some reference point at the origin. And so for quadratics, that reference point we're now going to call a vertex, okay? And if we wanted to, we could just look at this graph and say, okay, what is the x value that the axis of symmetry passes through? Okay, if I drop that vertical line there, what x value did I cross? Any ideas?
0. See,
Zero.
yeah, 0.
Yeah, 0. But notice this. The vertex is at 0, comma 0, right? And it has an x value equal to 0, right? It turns out that maybe one of the easiest ways to identify the axis of symmetry is just to find the vertex and then just write x equals whatever the x value of the vertex is. In this problem, it happens to be 0. Okay. But if we, if you have the notes for the one that we just had, the one we did on pencil and paper, our vertex is located at negative 2 comma negative 3. And we said that the axis of symmetry was negative 2. So later, if you're watching this video and you rewind the tape, maybe you'll make note of that. But we'll have some more examples here of finding the vertex and finding the axis of symmetry so that we can get used to this idea, okay? But we introduce these parent functions. And then we also introduce these rules for transforming the parent functions. Remember, if we added something to the graph, that can move the graph up or down. If we had parentheses and then added or subtracted something, that would move the graph left or right. If we multiplied a number in front of the parent function, like a times x squared, that would have the effect of stretching vertically the graph or compressing vertically the graph. And then there's one here that I didn't feature in the PowerPoint, which is if we have a quadratic function where we have like ax squared, right? If that is a negative a that's being multiplied by the quadratic function, that in the terms of transformations, we said that that would be a reflection across the x-axis. Well, if we reflect something across the x-axis, we're going to flip it upside down. Okay, so if we have a negative number that's being multiplied by the function, we know that that's going to be an upside down parabola, in which case the vertex will be a maximum, right? But if I have ax squared and that number in front happens to be a positive, then I know that my parabola is going to be right side up based on my transformation rules. And my vertex, which is going to be the lowest point of the graph, is a minimum. Okay? So like I said before, we're trying to marry some of the ideas that we saw in test one with some of these concepts for graphing quadratic functions. Okay, and we're going to get some practice here really quickly with some of these examples that I wanted to throw at you. Okay, so think of this like a mini quiz. All right, and we just want to refresh our memory of how these transformations work. So in this slide, I have um, a parent function, p of x is equal to x squared. So the parent of all quadratic functions. If I give you a manipulated or a modified function, like g of x is equal to x squared minus 4, can you guys tell me, if you recall, what is that minus 4 on the outside of the x squared? What is that going to do to the graph?
It's gonna go,
Be a negative.
Well, what do you mean by be a negative?
What's
Gonna
gonna
go
go
down
down?
Yeah, it's going to move the graph down. In back in test one, we said it shifts the graph down 4 units because we subtracted 4, right? So if we were to graph this, we expect that the parent function will have moved down, and now the vertex has shifted down, straight down to 0, comma, negative 4. Okay. Does that seem familiar?
yes.
Okay. All right. So we're just refreshing on these transformation rules because it's going to be a kind of helpful as we solve some of these problems. Okay, example 2. Same parent function. We're just dealing with quadratics in this homework assignment, right? So if I gave you g of x is equal to, in parentheses, x plus 3 squared, how does that plus 3 on the inside of the parentheses change or modify or move the graph?
Would
Is
it
it gonna
be
go left?
shifted to the right 3 times?
So
It shifted to the left 3 times.
Shift
it's
to the left?
it's going to shift to the left. Okay, and that, when you were studying this for test one, you might have been like, oh man, why does it shift to the left? And we'll talk about that in a moment. But yeah, this one is kind of counterintuitive. But one quick way that you can remind yourself is that when you're inside the parentheses, it's doing the opposite of what you're seeing. So if your brain is thinking plus 3 goes to positive 3, when you're inside the parentheses, it's doing the opposite of that. So it's moving to the left 3. We should see this graph move to negative 3. So we're going to shift our graph to the left 3 units. And that's exactly what we see when we graph this parabola. Okay. So yeah, so let's leave that there and we'll go ahead into the next slide. I think I have one more example here. All right, still trying to get reviewed up on these parent function, the transformations. Okay. Yeah, and Audra just went ahead and sent some modified notes for those transformation rules in the chat. If you want to download that set of the transformation rules, it looks like she added some of her own notes there. That can be really helpful. Okay. I haven't frozen, have I?
No.
Okay. Some of my features are not working. What's going on here? Hopefully I don't freeze. Okay. Dude, what's happening? Where's your car, dude? Okay. Let's see. Stop the share. That's not working. I think that Audra sent a computer virus through the chat and now my computer is blowing up. Oh, there it is. There was some other dialog box that was open. Okay. Something was happening. Let's get back over here. And just unfortunately, if you review this video, then just skip through the part where I have an aneurysm, okay? And here we go. I probably gave away the secret here, but okay. All right. This example says describe the transformation that's been applied to the function. So we have that same parent function. And if I gave you g of x is equal to 1/4 times x squared, how is that 1/4 multiplying into the parent function? How's that going to change the graph? What do we expect to see here?
Compressing the graph.
Yeah, that's going to compress the graph. So remember, if that number is greater than 1, then you're going to stretch the graph. But if it's less than 1, it's going to compress the graph. So, Alex sometimes uses this language of shrink, but I feel like shrink makes you think it's getting smaller from all sides. But when you think of it as compressing. And so like a hydraulic press, it should sort of explode out of the sides and get kind of wider. Okay. So because that's a fraction that we're multiplying by the function, we should shrink with really hardcore quotations there. We should shrink the graph by a factor of 1/4, which means we expect to see a graph that's wider here. So one thing that you might point out is that on the parent function, we have this point at 1, comma 1, and that has been crushed down so that the x value is the same. We still have that x value of 1, but now this y value has been shrunk down to 0.25, which is the same thing as 1/4. Okay. Okay, so if that kind of hurts your brain, it doesn't matter. You just need to think about this crushing and that the graph gets a little bit wider as we're crushing it, okay, or compressing it. All right. So with that review kind of in our rear view, kind of refreshed a little bit, now we can get back to talking about our quadratic functions because you're going to see quadratic functions that are written in what we call vertex form, but vertex form looks a lot like the format that I gave you guys for understanding how transformations work, right? So in vertex form, you have this maybe a number in front of the parentheses, and you know that that's the vertical stretch factor. We have this number that's either being subtracted or added inside the parentheses. That's going to shift our graph left or right, and that's kind of doing the opposite of what we think it's doing. So if it's a plus, it's going to shift to the left. If it's a minus, it shifts to the right. Okay. Then we have this other dial on the outside of our function, the plus k, which if we're adding a number, it's going to go up, and if we subtract a number, it goes down. So that's why I kind of wanted to review this because you've seen it before. We just didn't call it vertex form before, okay? But if your quadratic function is given in this form, then you can pick out what the vertex is going to be without having to calculate anything at all. You can just look at the graph, or I'm sorry, you can look at the equation, and the opposite of whatever this number is here. So if I have negative h, we're going to take the opposite of that, and that's going to give us the first coordinate for the vertex. Okay? So if it's a negative h, we're going to put a positive h for our vertex. If it's a positive h, we're going to put a negative h for the vertex, right? So it'll be the opposite coordinate for that first one. And then the k tells you the y coordinate or the second coordinate for the vertex, and that's going to be the exact same sign as what we see in the equation, okay? So again, it's going to make answering these questions in your homework like so simple if you let it, okay? So you don't want to overcomplicate it. We're going to do some practice problems here in a second where we just look at the equation and we just pick out what the vertex is, okay? Then if we can do that, we're going to also be asked to identify what the axis of symmetry is. But as I said moments ago, the axis of symmetry is always just that first coordinate of the vertex. So whatever the value of h that we put for the vertex, x equals that number will be the axis of symmetry. Okay. So there's some vocabulary here and some ideas here that maybe are a little bit cloudy, but these next couple of practice problems I'm going to give you, um, hopefully should clarify that, okay? So do you guys need some more time to write these notes down? I want to make sure that I'm not rushing through this too much.
Yes, can you give me a minute?
Yeah, just let me know when you're good.
Okay.
Yeah. Okay, cool. No time for questions. We're moving on to the practice problem, okay? So we have this practice problem. You're going to be given a function that's like g of x is equal to 3 times x minus 7 squared plus 4, okay? And what I really want you to get into the habit of doing is, if this is in vertex form, you should be able to tell me all of the transformations that have been applied to the function. So what does this 3 in front of the parentheses do to the graph?
Stretches.
It's going to stretch it by a factor of 3. What does the minus 7 do to my parent function?
Goes to the right.
Goes to the right by 7 units. And then what does the plus 4 on the outside of all of that do to my graph?
Up 4.
Up 4. Okay. So maybe I'll put an arrow like this to say that we're stretching with the 3. So the 3 stretches us. The negative 7 on the inside of the parentheses moves us to the right, even though that may be a little bit fuzzy right now. We might have some bombastic side eye on that one. But the plus 4 definitely will move the graph up. So like you should get into the habit of writing down those transformations so that this stuff makes sense for you. Because at this point, I feel like I'm asking you and the questions are asking you to understand what it is you're looking at and what you're doing. But like our brains can only hold so much information. That's why we have paper and pencil to write things down that our brains can't hold, okay? So we're putting that together. The transformation rule should be good, but most of the questions in the homework are just going to ask you, where is the vertex of the function located? Okay, and so I'm going to walk you guys through this one. Let me erase some of these markings that I put over here, just so it's not so busy. Okay. Now, on the previous slide, I said that the opposite of this number will be the first coordinate for your vertex. And then the exact same thing as this number, that positive 4, will be the second coordinate of your vertex. Are you guys okay with that? I'm going to put over here opposite for this one, same for this one. Okay. And so if you can identify that just by looking at the equation, great. You've just answered this question. 7 comma 4 is the location of the vertex. Okay. And so the questions in Alex are going to say, what's the vertex? And then once you put that in, the next question is going to be, well, what's the axis of symmetry? Write it as an equation. So can you guys tell me what the axis of symmetry is? I'll help you out. X is equal to what?
7.
That's it. X is equal to 7 is the axis of symmetry because it's the first coordinate or the x value of the vertex. And that's it, right? That's all you do. Whenever you're given the function in vertex form, it's so easy to answer these questions that you're going to question, is there more? Is there more I have to do? That's it. And like I've been telling you guys, let it be that simple because like we need to move on and do more complicated things. Okay? Any questions or comments about that? Okay. So the axis of symmetry we said is x equals 7. I'm going to erase this that I wrote because we have it in the PowerPoint slide now. And so if we were to graph this in a graphing calculator, like Desmos.com, I don't know if I have this in the PowerPoint, but if you go to Desmos.com, are some of you guys familiar with this, Desmos?
Yes.
Okay. If you go to Desmos.com and you type in exactly this function, g of x is equal to, you type in this whole thing into the graphing calculator, it's going to produce a graph that looks like this. Well, it's going to produce the green one. I put in the parent function in blue, okay? But based on everything we just analyzed about this function, we said, oh, this graph should be shifted to the right 7 units. And that's exactly kind of sort of where we find our graph. If we move from the vertex or at 0, 0 at the origin over to the right 7 units, and then we go up 4 units, we land at this new vertex, right? So it landed exactly where we said it would land based on the transformations and based on just taking the vertex from the equation. So those two pieces of information, they corroborate the same story, right? And then if you look at the green graph, which is our g of x, it's a little bit skinnier compared to the parent function, okay? And that's because it's been vertically stretched by a factor of 3. So if you think about stretching a rubber band, as you stretch it, it gets narrower, and the farther you stretch it, kind of the sides get more narrow, okay? So everything in the universe makes sense, right? These two pieces of information or these two storylines that seemed independent, they actually are telling you the same thing. And so that's really nice. I think that's a really beautiful and consistent thing about mathematics, that two different ways to answer the same question, right? Um, but, right, you get to choose which one's easier for you, okay? Doing the transformations to find the vertex, or just doing that thing by, taking the opposite of h and then taking the k and getting the vertex that way. But both of them are pretty straightforward, I think. So here's another practice problem. All right, again, I want you guys to get into the habit of describing all of the transformations that have been applied, and there are 4 transformations that have been applied to this parent function. So can you guys tell me what transformations are happening to this graph just by looking at the equation?
Okay.
Is one of them that we're reflecting?
Yes, so because we have a negative sign, we know we're going to reflect across the x-axis, right? So our graph should be upside down. So we should be eventually looking at a U-shaped parabola that looks like this, upside down. Good one. What else is happening to the graph?
Vertical stretch or shrink.
Vertical shrink, right, or compression, because this guy is a fraction, and that tells us that we're going to compress the graph. So if we're compressing the graph, it's going to be a little bit wider than its parent function because it's getting kind of crushed like a hydraulic press. Okay, so that takes care of those little like knobs or dials, right? We're dialing in the transformations that have been happening to the graph. What does this +3 do to the graph?
Shifts it left 3.
Yeah, it's going to shift to the left 3 units. And then finally, what does this -1 do?
Shift down.
It's going to shift that graph down 1 unit. Okay. So it might take like a second to just like write that down and sort of get your head on straight as you're jumping into these problems. And really, the Alex questions aren't going to ask you to go back and do these transformation rules and describe them. I'm just trying to get you guys into being thorough here and really thinking through the problem, right? Slow it down, think about what you do know, because sometimes you're confronted with the problem and you just draw a blank. But what I want you to do instead of drawing a blank is say to yourself, or take a breath and then say to yourself, what do I know? What is happening here? What do I expect to see? And then hopefully when you're doing that, the other stuff will come to you, okay? So we have this description of our graph. We said it's going to shift 3 units to the left because we have the plus inside the parentheses. It's going to shift down 1 unit because we have that -1 on the back side of the equation. It's going to be vertically compressed by a factor of 1/2 because we have a fraction there being multiplied by the function. And then it's going to be reflected upside down across the x-axis because of the negative sign. Okay. But Alex is just going to ask you, by looking at this equation, can you tell me what the vertex is for this parabola?
-3, -1.
-3, -1 is exactly right. Right? Because it's the opposite of that number inside the parentheses, and then it's the same as that number in the backside of the equation. Okay? So if we have the vertex, we actually have the axis of symmetry. What is the axis of symmetry as an equation?
X equals -3.
That's exactly right. You put those answers into Alex, you hit that check mark, and you move on with your life. Okay? But if you still feel a little bit reluctant to hit that check button, remember, you can always go to that desmos.com website, type in the full equation exactly as it's typed on the screen, and then you should get a graph that looks like this green one over here, right? And as we inspect this graph in Desmos, and I encourage you guys, when you're working on your homework in Alex, have a second tab open where you have the graphing calculator on desmos.com so that you can just check your work. Because sometimes we do things with math, we write some stuff down on paper, but it doesn't feel like I don't know if I'm right, right? How can I check myself, especially if math world is closed and you can't get contact with your professor? Go to Desmos. Use the tool to check yourself. We said that this graph was going to shift to the left 3 units, so it moved over to -3, and then down to -1. So that's exactly where we find the vertex now. We also said that the graph was going to shift or reflect and be upside down. And you can't really tell, but this green graph is a little bit wider than the parent function. Okay. And so the world makes sense, at least the world we've been building with these quadratic functions. Okay. Any questions, comments, concerns about those two examples? It really is going to be that easy, but I just want to see if there's any other questions or comments before we move on to some other stuff.
Can you comment again, where you said it's opposite of the inside of parentheses?
Yeah, so that's specifically when you're finding the vertex, right?
Okay.
So one thing that some students make a mistake of is sometimes we write the vertex form as a, and then we put x minus h squared plus k. And this is the way it's presented in the textbook also. And they say, oh, the vertex, if you just look at this equation, is going to be h comma k. But students will make the mistake of putting -h comma k. And they're like, oh, why is that wrong? Okay. It's because when you look at this function, whatever function's given, it's always the opposite of whatever you see there. So if this is a +3, your vertex starts with the opposite of that. So our vertex was at -3. And that should make sense because when we were talking about our transformation rules, before I said, oh, if I have x +3, this doesn't feel like it should go to -3, but it does go in the opposite direction to -3. Okay, so it's always going to give you the opposite of the sign that you see here. But this number on the outside indicating how low we're pushing our graph down, that number is going to stay the same. Okay, so opposite of what you see in the parentheses, and then the same number that you see on the outside of the parentheses. Did that clear it up?
Yes, thank you.
Okay, cool. All right. Hopefully those problems seem like they were easy to solve. And that's all well and good, but not every single quadratic function is going to be given to you in standard form. I'm sorry, in vertex form, right? Some of these quadratic functions will be given in standard form, and in standard form, we usually label the coefficients A, B, and C. So we don't have an obvious H and an obvious K here. The A is still the same, basically. And if that's a positive number, then we'll have a right side up parabola. But if that's a negative number, we'll have an upside down parabola for sure. But I don't have an H and a K here. So how am I going to find the vertex just using the equation without doing any graphing? Okay. Well, that's where we introduce a formula. Okay. And this formula for finding H should be pretty familiar because if you think about the quadratic formula that we use to solve quadratic equations, that was x is equal to negative b plus or minus the square root of b squared minus 4a ac all over 2a. You guys remember that from yesterday?
Yes.
It turns out that hidden in plain sight, part of that formula tells you the information about the vertex. This negative b over 2a, that gives you the first coordinate of the vertex. So what we can do is take this a and this b, whatever these numbers are, plug them into this little formula, and we're going to get that number that represents the first coordinate of the vertex. Okay. And then if you vaguely remember function composition from module 1, which is where we plugged a number into one function, did some math, evaluated it, and then got a new number, and then took that number and plugged it into a different function. That's kind of what we need to do here to find k. Because once we find the value of h, we're going to plug that back into the original function and evaluate it. So I'm going to, whatever h is, I'm going to plug that in here and here into the original equation, and that's going to give me k. So in textbooks, it's usually written as f of h is equal to k. If that feels like overwhelming right now, it kind of is a flashback to test 1 and to function composition, but you're going to see here in these next examples, we're going to have some practice, and hopefully it'll clear up some of the confusion. Do you guys need a little bit more time to write some of these notes down? I'm going to assume the silence is golden. Let's get into our first practice problem here. The thumb has spoken. Okay. First equation. We need to analyze the function below by answering some questions. Okay. We have g of x is equal to negative x squared plus 4x minus 1. And so sometimes Alex is just going to throw an equation at you and then start asking you questions, start sort of shaking you down and harassing you. Give me the information, right? Where is the vertex of this function? You're going to read those instructions and you're going to think to yourself, well, I don't know. Where do I start? Okay. And if this equation is in standard form, we start the way we start most quadratic equations in standard form. And that is by labeling what is A, B, and C. What is our coefficient A in this quadratic equation?
-1.
-1.
-1. What's B?
4.
Yeah, 4. What is C?
-1.
-1. And so when you're finding the vertex and your equation's in standard form, you just learned what the formula is. I'm going to put it on the screen. The formula to find H is going to be negative B over 2A. Okay? So what you want to do, just like with the quadratic formula, I mean, this is a lot smaller, but to be safe, rewrite it, but open parentheses wherever those variables are. So B is going to be an open set of parentheses, and then we're going to do 2 times something, okay? And so if you do this every time, I hope that you make fewer mistakes when you're plugging in what number into what position, right? So what number goes on top of our fraction?
-4.
Right. So the negative is from the sign that's in the formula,
So,
right? But we're
yeah.
just plugging in 4. I just want to be clear about that.
Okay.
Because like if you tell me we're plugging in -4, I would be tempted to put a second negative, right?
Gotcha.
So we're just plugging in 4 because that is what B is. Okay. What are we plugging in for the lower parentheses?
-1.
-1, right? Are you guys okay with that?
Mhm.
Okay. This fraction, just put it into the calculator. I was gonna say, can anybody do this in your head? But like, we don't have time for that. We have to like solve other more thoughtful questions. Remember, we can type this into our calculator by hitting alpha, y equals, get your fraction, and then type it exactly the way you wrote it. So we're gonna put a negative, parentheses, 4, close parentheses. That's the numerator. The denominator is going to be 2 parentheses -1, close the parentheses, hit enter. What did you guys get?
2.
2.
Boom. That's the first coordinate, the H of our vertex. Questions, comments? Okay. But our vertex needs to be H comma K, right? So we need to get that K value. So this is a two-step process. To
Mhm.
find K, what we're going to do is take the original function, g of x, and I'm going to plug what into that function?
2.
I'm going to plug the 2 into that function. Okay. So when I evaluate this function now, I'm looking at the original equation here. And the original equation was negative x, so negative parentheses squared, plus 4x, so I'm going to put a parentheses there, minus 1, right? And then what am I putting in the parentheses?
-1.
4.
No, I'm sorry. 2.
2. Sorry.
We're putting 2. That's what these instructions are telling us to do, right?
Yes.
Yeah. So we need to put 2. And this is why like it might seem like a simple question that I'm posing to you guys, but I just want to make sure that we're getting, clear answers here. We're taking whatever number we got for H, right? So we don't need A, B, and C anymore because we just use them to get the H. And then once we got what we wanted, we're going to plug that into the original function, and that just happens to be 2. Okay. So again, this is a situation where you can try to evaluate this by hand, but um, I've been teaching this a long time. I'm going to keep on saying that. I've been teaching this for a while, and I find that students, when they try to jump in and do this by hand or do it in their head, that they make very common mistakes. So put it in your damn calculator and like let the calculator do it for you, okay? So we're going to type it out exactly the way we wrote it. Negative parentheses 2 squared plus 4 parentheses 2 minus 1. And what are you guys getting?
3.
3.
3. Okay. So don't overcomplicate it. Maybe this version of finding the vertex is a little bit more complicated than when we have a vertex form equation, but we were looking for H. We use that to find K. And now that we have both of them, we can say our vertex is just 2 comma 3. Are you guys okay with that?
Yes.
Okay. And the axis of symmetry is what? X is equal to
2.
2.
2, right? Because it's just the first coordinate of your vertex. So once you have your vertex, you know what the axis of symmetry is, okay? All right. I'm going to clear the screen right now because I have these animations in the PowerPoint. So I show you, and I tried to color code in those animations. Um, I tried to color code some of the things, like the coefficient A was this negative 1, so that's why I put it in blue. And then B was orange, so I kind of kept that consistent here. And we found our H value that way. Then we took our H value, plugged it into the original function, and we found K. Putting it together, we found our vertex. Okay, and when you graph this thing in Desmos, just to double check yourself, you should see this parabola that's upside down, and the vertex is exactly where you think it should be at the very top of the graph. We have 2, 3, right? Can anybody tell me why this graph is upside down?
The reflection.
Yeah, because we have this negative sign in
Negative.
front of the x squared term, and that told us automatically, even before we graphed it, that it was going to be an upside down parabola. Okay. Now, is this vertex here, is it a maximum or a minimum? Yeah, it's a maximum. Why is it a maximum?
Because it's facing upward.
Well, what is facing upward?
The vertex.
Yeah, so the way I would the way I would say it is that the parabola is facing downward, right? But the vertex is on top. So if it's on top, it's a maximum. Okay. But I know you knew what you were saying. Okay. So as long as that makes sense, I just wanted to do some little quizzes here to make sure that we're understanding all of these concepts and how they work together. Okay. All right. I think I have another practice problem in here. Okay. So what I want to do is give you guys like a minute or two. I'm going to awkwardly stand here while you guys find the H value using that formula and then find the K value. If you can tell me what the vertex and then the axis of symmetry are, I'll be happy. So take about 2 minutes to do that. And if you need that formula, I'll write it here. H is equal to negative B over 2A. And then as soon as you get your answer for H, you can put it in the chat if you'd like. Or if you want to hold off until you have the full vertex, I'd be cool with that as well. Is this going smoothly or is anybody on the struggle bus out there? I see we have one answer so far, but Does anybody need some assistance, some support? You guys ready for me to jump in, or do you want some more time?
Three.
Okay. I think that's enough time. Otherwise, the video is going to have this awkward pause in it. So if you watch that video, if you watch it back, just fast forward through this part th where we're just paused. So to find h, we use that formula, negative b over 2a. We plug 2 into the top of our fraction, right? So we have negative 2. And then 2 times 1/3, that's going to be a, right? And I know that, when you formulate this one and you write it down on paper, it's going to feel maybe a little bit scary because we have a fraction. Just remember, you have this for a reason. Use that calculator trick to make a fancy fraction. And the nice thing about those fancy fractions is that you can put a fraction in the denominator of a fraction, okay? So my recommendation is always type that into the calculator exactly the way you wrote it down, parentheses and all, and then you should be safe. Okay. 9 times out of the 10. The one time out of the 10 is probably you're making a mistake or you're putting a typo in there. But like, who among us has not fat fingered something wrong in a text message to a friend, right? So like, don't beat yourself up too much about it. Just double check, put it in the calculator again, and see if you get the correct answer, right? So we should have gotten -3 for the h value there. Then taking that -3 and plugging it into the original function, we should get a -5, right? And again, once you set it up with the parentheses, you do not have to do that by hand. Again, most times I notice that students tend to make mistakes when they're going through PEMDAS, okay? Use the calculator for that, get that -5, and then we can put it all together because like we're trying to get the big picture here, not the little mathematics, okay? So -3 comma 5 is the vertex, and the axis of symmetry is just x equals -3. If we were to graph this, you can see that dashed line that I have cutting through the middle of my parabola is cutting through the x value of -3. That's the axis of symmetry, which is the same as the first coordinate for the vertex. Okay. Some other fun facts that you might point out is that this graph is right side up, right? We know that because the a value, even though it's a fraction, it's positive. So the graph is positive with us. It looks like a smiley face. Positive means smiley face, okay? Um, then maybe you might say to yourself, well, is the vertex a maximum or is it a minimum? And because it's at the bottom of the graph, you know it's the lowest point, it's the minimum value. Okay? Any questions about that example? Okay. So up to this point, all we're really doing, and like the main thing that you're going to see in the homework is it's going to throw a function at you. Maybe it's going to ask you to graph it, but it's going to ask you to graph and find the vertex, find the axis of symmetry. So if we can graph things, if we can find the vertex and the axis of symmetry, I would say that you're about 50% of the way of completing this homework assignment. There are a couple of other questions that you might run into that you do need to be aware of, and that is the fundamentals of graphing. Remember when we were graphing linear equations, those straight line graphs, and I said, oh, well, we need to be able to find the y-intercept and the x-intercept, right? So like, let's just look at this graph that we have on the screen right now. I can see that this graph seems to be crossing the y-axis, which is right here, at 0, comma, -2, right? And if you have a really pretty graph, it should be very easy to pick out the y-intercept, okay? The x-intercepts, because the x-axis is over here, look like they're not quite at -7 and not quite at 1, right? So that would be like maybe -6.9, comma 0, and maybe that's 0.9, comma 0 over on the right-hand side. But there are algebraic ways to use the equation to find the x and the y-intercept, and so that's the next topic that we need to broach, okay? So to continue analyzing these quadratic functions, we're bringing back this idea of can you find the y-intercept and can you find the x-intercept, okay? This is the kind of thing where I think that if we just learn by doing, it goes a lot more smoothly than me just sitting here and kind of spitting definitions at you and like thinking through the problem verbally. We really need to see this for it to like become viscerally or for it to viscerally make sense to us, right? So just a vague definition that we have from the past is that if we're looking for a y-intercept, the y-intercept by definition, regardless of what function we're dealing with, always has an x value of 0. So I'm going to take my x value of 0 and I'll plug it into my function, and that will give me my y-intercept. Okay? And we'll see that in a second. Then we had this definition when we were looking at linear equations that x-intercepts always have a y value of 0. But since we've switched to using this function notation, f of x, we don't have y's in our equations. We have f of x equals this, g of x equals that, h of x equals something, but we haven't had a y in a while. What you have to remember is that the function name, f of x, is the same thing as y, okay? So we'll see that I'm going to replace this whole thing with 0 and then solve an equation, okay? But again, it's one of these things where it's only going to make sense if we jump in and do, so we're going to dive into the deep end here, okay? You will have to pay attention though, because not all quadratic functions will have x-intercepts. And what I mean by that is, look at this graph over here on the right. This one has 2 x-intercepts, right? The places where the graph is crossing the x-axis at -2, comma 0 and at 3, comma 0. But imagine that I use a transformation and I said, what if we moved this entire function all the way up so that it's no longer crossing or even touching the x-axis? Well, we might run into some graphs that look like that. And in those cases, we're not going to have x-intercepts, okay? So we'll sort of talk about some examples here where that might happen and what to look out for, okay? So first, and this is super important, I think, the y-intercept is always going to be the easiest thing to find, okay? Because by definition, all y-intercepts have an x value of 0. So all I need to do is plug in 0 wherever I see an x in my equation. Now this equation happens to be in standard form, but even if it was in vertex form, all I'm going to do is plug in 0 for x and then evaluate that in my calculator, okay? So what I'm really doing is finding g of 0, and I'm writing down 3 times 0 squared plus 3 times 0 minus 18. Are you guys okay with that? So if you guys are okay with that, then go ahead and put it in your calculator. But the reason why I think that it's kind of fun to find the y-intercepts is because if it's in standard form, What's 0 squared? Yeah, it's just 0. And what's 0 times 3? So that cancels out. And then what's 3 times 0?
0.
So that cancels out. So then what is my x-intercept then? I'm sorry, my y-intercept.
Negative 18.
Yeah, negative 18. And that's really nice. So I now know that g of 0 is equal to negative 18. Right? So I didn't necessarily need to use a calculator for that. If you are kind of insecure, and there's nothing wrong with being a little bit insecure at times, if you're a little bit nervous, go ahead and type that whole thing into the calculator. Either way, you're going to get that negative 18. So the y-intercept has two coordinates. It has an x value, it has a y value. What's the x value that we just used?
0.
So the first coordinate is 0, and then the second coordinate is negative 18. And that's it. We found our y-intercept. Any questions, comments?
No.
Okay. If you go through the PowerPoint, if you watch the video on your own later, I have the math. It kind of appears magically here, but it's very simple math, and that's why finding the y-intercept is always going to be way easier than finding the x-intercepts. Okay. Once you find the y-intercept, what I highly recommend is you go over to that second tab where you have Desmos open, right? You graph the equation. You should get a graph that looks like this. And if you sort of scroll down until you see where the graph crosses the y-axis, it's exactly where you think it should be, at 0, comma, negative 18. Okay? So again, we're using Desmos just to check ourselves, but you want to be careful that you're not using it as a crutch, right? You want to make sure that you understand what's going on in the math and not using Desmos to get your answers, because you won't be able to use Desmos on the test. Just as a double check when you're going through the homework or the review. Okay. So that was the y-intercept. Now we have to find the x-intercepts. And the x-intercepts are going to be a little bit more complicated. So I want to do the x-intercepts on paper because, well, again, I think that seeing a human hand work these out is a little bit better than seeing some PowerPoint animation. So g of x is equal to 3x squared plus 3x minus 18. And then we shift on over to our magical document camera. Okay. And then we zoom in a little bit so that you guys don't have to strain your eyes too much. Okay. All right. Find the x-intercepts. Okay. So whenever I write this problem down or this question down, I always put the x-intercepts part with the s in parentheses because sometimes you have two x-intercepts, sometimes you just have one, and then other times you have none. So if the x-intercepts exist, at most you'll get two of them. Okay. But the way we start this off is that you want to set the y value equal to 0, but you have to remember that g of x is the same thing as y. These guys are interchangeable. And since we want to set this y equal to 0, and we don't have a y in our function, what we're going to do is just replace this g of x business, the whole thing, we're replacing with 0. Okay? This isn't the same as when we plugged 0 into the function. We're just replacing this whole thing with 0, and then we have an equation, 3x squared plus 3x minus 18 equals 0. Okay, so we went from having a function to now we have a quadratic equation. Okay, and do you guys remember how to solve a quadratic equation? Yeah, there we go. Any ideas what the first step might be? And don't freak out just because the zero is on the left-hand side. We could put, this whole thing is equal to 0 on the right-hand side. Doesn't make a difference.
Is
We're
it
gonna
turning
do,
standard form?
yeah, I mean, it is in standard form though, isn't it?
Yeah, it just kind of like
It's just
this.
kind of flipped around. Okay, so like if you don't like it flipped around, then you're perfectly fine to do this. It's kind of an extra step, but if you want to flip around, that's perfectly fine.
No, that's fine. We could do it like that.
No, we're already doing it.
Is this where we do the A times C?
Yeah. So you have to go back into your arsenal of how do I solve quadratics? And so you have those three methods. One of them is factoring so that we can use the zero product property. So if we know we have three terms, then we're going to do the AC method to factor this, okay? The second method for solving a quadratic, it is by taking square roots or using the square root property. But we can only use that if we didn't have this 3x term in the middle, right? Because if that were the case, we would just move this 18 over to the other side, divide by 3, and then get the x squared by itself. But again, if we have that the 3x term in the middle, we can't do that one. Okay. The third thing we could do is just say, I give up, I'm using the quadratic formula, and then bust out that thing, and then plug some numbers in and go from there. But I think you guys probably need some practice with factoring. It's not going away, so let's factor this, okay? So A is equal to 3, B is equal to 3, C is equal to negative 18. Do we want to start this off by doing the AC method, or do we want to do something else real quick? Does anybody know what I'm hinting at here?
Factor out the 3x squared and the 3x.
So we can only factor a common factor out if all of them have a common factor. And so what number divides into all three of these terms evenly?
3.
3.
3.
So it might seem like the silliest, littlest move to make, but it's going to make this a lot nicer. So if I factor out a 3, I should be left with x squared plus x minus 6, okay, equals 0. Are you guys okay with that?
Yes.
Okay, again, the reason why I don't want to just jump right into the AC method is because 3 times negative 18 is going to be a kind of a bigger number, and that means it's going to have a lot of factors. If I can take a GCF out, then I'm just going to multiply 1 times negative 6 to start my AC method, right? So that's going to be a lot easier because 1 times negative 6 is going to be negative 6, right? What are all the factors of 6?
1 times 6,
Thank you. 1 times 6.
2 times 3.
And that's all the factors of 6, right? So I know that some of my students in my face-to-face class are still struggling a little bit with choosing the right factors here. But remember that we want to multiply the factors so that we get negative 6. And we want to be able to add those two factors together to get this positive 1 that we have here as our B term, right? Our B coefficient. So which factor pair do I need to choose?
2 and 3.
I need to choose 2 and 3. And then what are the signs on those bad boys?
2 will be positive, 3 will be negative.
Are you sure?
Well, let me see. To get a negative 6,
No. When we add them together, we're trying to get a positive 1.
positive 1. I'm sorry.
So it means that the 2 has to be negative.
2 has to be negative.
Okay, so like I like to focus on this second condition, the addition one, to make sure that I get that positive 1 first. And then the first condition, negative 2 times positive 3, gives you the negative 6. So like that's okay. We picked correctly and we got the right signs on those. If we choose the wrong signs, we're going to mess this thing up before we even start, right? And we haven't even really gotten into it yet. So make sure you take a little bit of extra time there. So now I'm just going to focus on this trinomial that we're factoring. I know that we have a 3 here, but it'll come back to play once we're done factoring this stuff. So we have x squared minus 2x plus 3x minus 6. And now we can factor by grouping. Okay, zoom out a little bit. So what do these guys have in common, these first two terms?
X.
X.
Yeah, they have a same x. Okay. Scandalous. Okay. And now what do we need inside the parentheses to continue?
X minus 2.
We need x minus 2 because x times x gives you x squared. X times negative 2 gives us the negative 2x. Then we can move on to these two terms. What is their greatest common factor?
Three.
3.
3.
Positive 3. So we're going to put positive 3, open up some parentheses, and then what goes inside the parentheses?
X minus 2.
X minus 2 for two reasons. One, it has to match this other parentheses, but two, if we distribute 3 times x, we get 3x. 3 times negative 2, we get the negative 3, so that worked out. Okay, which means that our factorization is x minus 2 and x plus 3. It doesn't matter what order you put those in. And then we can't forget that we have this 3 over here. Okay, so if we were just factoring, those would be the factors. Pero we're not just factoring, right? We have to completely solve this equation. That's where we bring in the zero product property. Okay. And the zero product property says that if we have some factors here that have a variable, then either this factor that has an x, x minus 2 could possibly be equal to 0, or x plus 3 could possibly be equal to 0. That's the only way we're going to multiply some stuff together to get a 0, right? This 3 is never going to be 0, so I don't really have to worry about it. You can just cross it out. If we have a constant that doesn't have a variable, doesn't matter. It's not going to change. It's never going to be 0. Okay. But if I set my factors, the ones that have the variables, equal to 0, and then I solve these equations, what do I need to do here to get the x by itself?
Plus 2.
X is equal to positive 2 in that case, because we're adding 2 to both sides, right? So there's one solution to my quadratic equation. And then my second equation, how do I solve this one?
Minus 3.
Minus 3. The 3's cancel out. And then we have x is equal to negative 3, right? Okay. So this is where we don't want to lose the forest for the trees because, for the last, it feels like eternity. We've been studying how to solve quadratic equations and putting all these things around. But remember, those are tools that we're using to analyze quadratic functions. We started off with this function and we were being asked to find the x-intercepts. Okay. And when we got through this process, we found x values. These give you the location of those x-intercepts because this is going to say, oh, x is equal to 2. That really means that my x-intercept is at 2, comma 0, since that x value is at 2. This is one x-intercept. And then this x-intercept is negative 3, comma 0, again, because that negative 3 is the x value. And there's our second x-intercept. So when you put this into Alex, it's going to ask you for those two x-intercepts. If you make some sort of mistake where you say, oh, my x-intercept is 2, comma negative 3, this doesn't make any sense because our ordered pairs are x, comma y, not x, comma x. Okay, so don't make this very common mistake. It kind of looks like a dead guy. I'm going to keep those x's for the eyes. We don't want the dead guy, okay? We want x comma y. And when we started this whole thing out, we said that the y value was equal to 0. So we let those y values stay 0. Okay. Questions, comments, concerns about that process? I know what you guys are thinking. It feels like a lot, right?
Yes.
Yeah. But just think of it this way. Well, 2 points actually. One, you guys chose to take this class in 8 weeks, so it's gonna suck, right? But the second thing is that, if you're keeping up with your studies, we've been hammering away at these quadratic functions all week, okay? And so hopefully, quadratic equations rather, right? We've been solving quadratic equations for the last few days. And so hopefully some of it is sticking. If it's not feeling like it's clicking, again, I think I gave a rant to you guys yesterday. You don't want to let the perfect be the enemy of the good. It's not an all or nothing situation when we're learning this. You have to be honest with yourself and say, how much do I get this? Give me give me a number between 0 and 100. And I guarantee you, if you're like at a 50, a 60, a 70 in terms of what you think you understand, then you're in a good position, but you're not at a 0, hopefully. Okay. Um, if you are at a 0 or at a low sort of confidence level, then make sure you're reaching out and going to Math World. Uh, and this actually brings me to my next point. Math World is going to be open tomorrow. Okay, so it's a Friday. If you check on the Math World link in Canvas, there are random Fridays that they're going to be open, and tomorrow is one of them. Okay. And I think they're going to be open from like 9 to 5 p.m. So if you're working on the homework or have some time to work on the homework, pop into a Zoom session with those guys. I think that it's going to be Pete or Gilly working from home, and they'll be in the Zoom chat to answer any of the questions that you guys might have about solving quadratics, analyzing these functions, finding x-intercepts, okay? So you're not alone. Just make sure that you're utilizing that assistance, and that you're not saying something like, "Oh, I'll just do this on Monday." Because if you put it off, well, we just don't have enough time in a 8-week semester to put off anything. So make it a priority. Okay. That being said, one example is probably not good enough, right? We want to see another example. Okay. Well, in the PowerPoint, if you go through it, I run through the process of finding that x-intercept or those two x-intercepts that we just found. Okay. We set our entire equation equal to 0. And then we solve that quadratic equation. And here I run through the whole AC method. I didn't show the scratch work of multiplying A times C. I assume that you can do that stuff, but I factored it the exact same way we did on paper. So if you need to run this back when you get to the video later, please do so. But we get our -3 and 2. Then when you answer these questions, you find the y-intercept and you find the two x-intercepts. Remember, open up that second tab with Desmos, graph your function because we should be looking at a graph that looks like this. And if you look at it, the x-intercepts and the y-intercept are exactly where we predicted them to be. And look there, I gave you the link for desmos.com graphing calculator in the PowerPoint. So if you forget, where is this website where the magical graphing calculator is? It's right here, okay? Let's jump into another example. We'll start off by finding the y-intercept because it's the easier thing to do, okay? So if I need to find the y-intercept, what do I have to do? Feel free to look at your notes on the last example.
Insert the X for
Insert 0.
0.
Yeah, insert 0 for x, right? So by definition, that's all we have to do here. So if I replace this x squared with a 0, what is my y-intercept going to be?
12.
Just 12.
No.
Right? So if I run through the mathematics and I write this down, I replace the I replace the x with 0, and the only thing that remains is the 12 when I'm done. So my x value was 0, my y value is this 12. And then if I graph this in Desmos, that x-intercept should be in the correct place. Okay. Then to find the x-intercept, I can just set my function h of x, set that whole equation, the negative x squared plus 12, set that equal to 0. So again, I think that the x-intercepts tend to be harder, so I'm going to switch over to the document camera so we can work this out on paper and not just follow along on the PowerPoint. Okay, so there's my function. All I'm going to do is put negative x squared plus 12 and then set the whole thing equal to 0. Okay. Now, we have a quadratic equation. This one looks a little bit easier. We're missing a term. Which technique do we want to use to solve this quadratic equation? Or what is the first thing that comes to mind as far as like digging into like solving this thing? What's the first step you guys want to take?
Get
Minus,
the x by itself.
minus 12.
Yeah, you can minus the 12. Or you guys remember when I said that I like to keep my x squared positive?
Yes.
Yeah. I think it would be easier to just add the x squared to the other side. Okay. Negative x squared plus x squared, that cancels out. And I'll have 12 is equal to positive x squared. And I know that you guys probably don't like having the x squared on the right side, but it doesn't make a difference. Okay. If you want to, you can do that inversion and sort of flip it around at this point and put x squared equals 12. It doesn't make a difference here, but I just wanted to keep the x squared positive. And I'll explain in a second why I think that's a little bit easier. But now, how do I cancel out the square?
Divided by square.
Not divided by, right? So we got to like hold back because I know we maybe on autopilot we're saying divide by because that's usually what we do. But to cancel out the square, you're correct.
Square and both.
Square root.
We square root both sides. Okay. So when we square root both sides, that's what we say we're applying the square root property. Okay. And we know the square root cancels out the square. So I'm going to have x is equal to, and then on the opposite side of the x, we always put a plus or minus, and then we simplify the square root of 12. Right? So it might look a little bit different because it's on the wrong side of the equal sign, but the same process. Okay, so is this a perfect square?
No.
No, so that tells us, hey, we're going to have to make a prime factor tree for 12. So 2 times 6, 2 times 3, and then this is just 2 squared times 3. I'm whipping through that a little bit fast, but are you guys with me there?
Yes.
Okay. Then I'm taking the square root of 12, so I'll just take the square root of these factors individually, and then if I have a square root in the square, those cancel out. So then this should be equal to plus or minus 2 times the square root of 3. Okay, so if I needed to write my solution set for this, then that's going to be negative 2 root 3, comma, positive 2 root 3. Okay, this would be the solution set. However, we're not finding a solution set for this equation. What we're trying to find are the x-intercepts. And these, in our solution set, are our x values, right? So our intercepts are
Negative.
negative 2 root 3, comma 0. And so I'm putting a little comma here. Positive 2 root 3, comma 0. Are you guys okay with that? Okay. So you might say to yourself, like, if I had to graph these, oh God, that might be terrible, right? I don't even know what this number is. I've never seen a thing like this in my life. Okay. That's fine. That's what you got a calculator for. Okay. So like this number here, we could just get an approximate value, right? If we're just graphing by hand or just playing around here, because we know we like to play with numbers so often in life. Just put it in the calculator, -2 times the square root of 3. And then if we're just making an offhand estimation, it's about -3.464. So you could think of this as approximately equal to -3.464 comma 0. And then this one is just going to be positive 3.464 comma 0, since they're basically the same number with the exception of the sign. Okay. What you're going to put into Alex, though, is the exact x-intercept. So this is what Alex wants, and what Alex wants, Alex gets. So uh, that's what we need to put in for our answers, okay? Any questions or comments about that process? Okay. Let's go back to the PowerPoint. And trust me, guys, we're almost done here, so. If you review the PowerPoint, I have these notes where I move the negative x squared over to the other side. Okay. And I did want to make a point here because, some of you guys are going to be tempted to subtract the 12 over the other side. And that's perfectly fine and legal. Okay. If we did that, we would get negative x squared equals to -12. But this is what I was talking about, like whenever you have a negative x squared, all the negative signs start to get a little bit confusing, and students tend to forget that to cancel out a negative in front of the x squared, you can divide by -1. So if you do it this way, you just have the extra step of trying to cancel out these negatives, and then you get x squared equals +12. And then we're right exactly where we were before. But it took us an extra step or two. Okay. So that's why I always recommend moving the x squared to make that a positive, because I think it just goes a little bit more smoothly. Either way, if you're running through this process correctly, we get that square root of 12. We simplify that using a prime factor tree like we were doing a couple days ago. And then we should be able to get our x-intercepts. Then, because we might get lost in the forest a little bit, we want to say, okay, we have our answers, we have our y-intercept, our x-intercepts. How do I know that these are correct? We go to Desmos, right? And so Desmos said, guess what? Our y-intercept was at 0, 12. That's exactly what we calculated. And then Desmos is saying, oh, your x-intercepts are at -3.464 and +3.464. But that doesn't look like this, right? So I do have to say there are some limitations whenever we have any kind of technology. Desmos is going to round these radical expressions to 3 or 4 decimal places. Okay. So if you see a weird decimal here and that's not what you calculated or simplified when you got a radical, then just put those radicals into the calculator so that you can figure out what does it equal in a decimal form. Okay. And that's one way that you can check yourself. Questions, comments about this process? You guys probably going to need some more practice in the homework, right? Okay. Well, I don't want to abuse you much longer here. So the good news is we only have 2 slides left. Okay. And that is, I mentioned that sometimes we get no x-intercepts. Okay. There's an easy way to tell when you're going to get no x-intercepts. That means that your parabola does not cross or touch the x-axis. Okay. And that is when we get imaginary numbers for our x-intercepts. So if you are working through one of these problems and you're given an equation, you're always going to find a y-intercept, okay? there will always be a y-intercept. Okay, I'm putting 10 toes down when I say that. There will always be a y-intercept. However, depending on if your graph is floating very high up or is pushed very low down, you may not have x-intercepts. Okay, so let's look at this example really quickly. F of x is equal to x squared plus 4. Okay. If we were to go through the process of finding a y-intercept, well, that's easy because we just need to find f of 0 where we plug 0 in for x. Okay. And if we do that, we'll get 0 squared plus 4. So f of 0 is just equal to 4. Are you guys okay with that?
Yes.
Yeah, so our y-intercept is going to be 0, comma 4. That's nice. Okay. Y-intercept. Every time I write int, I think of how British people say in it. If you're familiar with British comedy or British people in general. Sorry, the ADHD got me. Then when we try to find the x-intercepts, right? We have to take this function x squared plus 4 and set that whole shebang-a-bang equal to 0. How do I solve this equation? What's the first step?
-4.
Yeah, -4. No need to be shy here. It's a pretty respectable and small quadratic equation. So we have x squared is equal to -4. And then what do I do?
Square root.
Yeah, use the square root property, take the square root of both sides. So I'm going to get x is equal to plus or minus. Do you guys know off the top of your head what the square root of -4 is?
2, but
Not.
it's gonna be 2i.
There we go.
Yes, 2i.
2i, because we have an imaginary number when we take the square root of a negative, okay? 4 was a perfect square, so this is kind of an easy example. So like, I would be telling you guys that the x-intercepts are -2i, comma 0, and +2i, comma 0. However, if we look at the graph in Desmos, we have this parabola. Does it have any x-intercepts?
No.
Yeah, it
No.
doesn't cross the x-axis at all, right? So how do we know when our graph is not going to cross the x-axis? That is
That's an
exactly
imaginary number.
that's exactly when we have an imaginary x-intercept, right? So when we have an imaginary number here, we can say there are no x-intercepts, and Alex will give you a button where you could just type in the word none. That looks like now we, but that's a none. N-U-N, there are none. Okay. Are you guys okay with that? Questions, comments? Okay. So if you're okay with that, there are 2 Edpuzzle videos in Module 2 that talk about imaginary numbers. And what it turns out that like when you have imaginary x-intercepts, you need a third dimension to actually show where the graph crosses the x-axis. But in this class, we're just dealing with flat graphs. We have an x-axis, a y-axis, and we're not going to have a third axis, okay? But if you watch those videos, and they're very short, and I think they're kind of entertaining in like a historical sense, if you like watching documentaries on TV, they're just like a 6 or a 5-minute video, maybe 10-minute video on a little bit of a primer on imaginary numbers to throw some fun your way. Okay, fun is maybe a term we're using loosely here. But that is going to be it. Okay, so we are done with module 2 now. Okay, so I urge you, when you have some time, watch these Edpuzzle videos if you haven't already. But the material that we've covered today will get you through assignment number 14, which is the last homework assignment in Alex for this unit. Okay, so when we come back on Monday, we're going to give you guys an opportunity to work on the review for test 2. And if you've already done the review, there will be time to work on the practice test. Okay. If you're already ahead of the game and you've completed those by Monday and you feel like, oh, I'm going to dip out, just shoot me a courtesy message to let me know you're not going to be there on Monday. But and also, if you're ready to take the test earlier, and I think a couple of you might be, then feel free to send me that message and I'll send you the password for the test early as well. Okay. But for anybody else who's just like holding on for dear life, okay, what you need to do over the weekend is just make sure that you're getting caught up on any homework assignments. So this week, we should have gotten through homework assignments 11 through 14. And so if you're caught up or get caught up, then that's as far as you need to go, right? There's no additional homework this weekend, but it is optional if you want to get ahead, because things come up in life that sometimes we can't predict. But if you want to get ahead, you can start in on the test review for test 2. Okay. I do not have anything else for you guys today, so we're going to leave it there. So if you want to stick around and ask some questions and chat with me for a little bit, you can do that. Otherwise, I will just see you guys on Monday.